Hi, and welcome to my first video on using Microsoft Excel for chemical engineering calculations. In this first video, we will cover how to perform material balances using Excel. This can be used when dealing with a system that contains many chemical components or many unit operations. We will first discuss the three main units which make up the basis of these calculations in Excel, and then I will demonstrate how they can be used to solve two advanced problems. Okay, to begin, we will first look at an example on how to use the basic mixer unit operation. We can see the governing equation here. The unit operation, we can see the governing equation for the mixing unit, which says that for a given component I, the sum of said component's molar flow rate or mass flow rate in each stream J is equal to the outlet flow rate for component I. So to demonstrate how this can be done in Excel, I have an example where I am interested in mixing water, sugar, concentrated orange juice to make orange juice beverage. And we are interested in finding out not only the outlet flow rate of the mixture, but also the mole fractions for each component to ensure the orange juice meets certain specifications. Okay, so as I said before, we first need to calculate the outlet flow rate of each individual component. We can do this using the sum function in Excel, which I will do now. We can then obtain the rest by simply dragging at the edge of the cell like this. Finally, we can get the mole fractions of each component in each stream by dividing the components by the total molar flow rate in each stream like this. Okay, so this was a simple example on how you can set up an Excel sheet to perform these kinds of calculations that you could probably do by hand, but it can be expanded very easily to perform calculations with many components and or streams. Next unit we will be looking at is the separation unit. That can be used to represent any unit where you have a stream splitting into two streams. Examples include distillation, absorption, evaporation, and cyclones. So the idea behind this is when we are interested in finding out how much of each component will be leaving for each individual exit stream based on a particular split fraction. Split fraction, this symbol here, is defined as the percentage or fraction of a component in the inlet stream that will be present in the top stream. However, you can define it based on the bottom stream also. It's up to you. Okay, so to demonstrate how to do this, we will look at a distillation process in which we are interested in removing propane from a crude oil mixture, and we will like to have 99% and 0.5% of the propane and isobutane respectively in the top stream, and 0% of the heavy components in the top stream. So based on the governing equation, we can find the components' flow rates in the top stream easily by using the governing equation, which is simply multiplying the component's flow rate into the separator by its required split fraction, which I will show now. We can then find the amount in the bottom stream by subtracting the total amount of your components originally in the inlet stream by the amount calculated in the top stream, like this. And just like in the previous example, we can calculate the mole fractions for each component in all the streams by dividing the amount of each in a particular stream by the stream's total molar flow rate. Okay, so we have now come to the last unit, and then I will show you two examples on how these three basic units can be used to perform more advanced material balance modeling problems. So now we will be looking at the reactor unit, and what it does is calculate the molar flow rates of reactants and products based on a specified reaction conversion alpha and stoichiometric ratios based on the governing chemical reaction formula. So we will showcase this unit by looking at an example. For this example, we would like to figure out the composition of the outlet stream for a methanol steam reforming reactor, where the single pass conversion is based on methanol and is 25%. Okay, so let's do this problem. Okay, so all I did was enter the governing equations in the top here into this cell here. The most important thing to remember is that the governing equations changes for reactants and products. For reactants, there's a negative sign, and for products, there's a positive sign. Okay, so for our first advanced example, we will be using several separation units in sequence to represent a distillation train for separating a crude oil mixture into several high purity fractions. The required split fractions for each unit is shown in the sheet already. To solve this problem, we will solve the first separator exactly like was shown previously, which I will do now. The new outlet stream for the next separator, we can solve for the entire train very quickly by dragging the entire separator one block across, which I'll show now. Then from these values, you can probably perform energy balances or preliminary distillation column sizing, which I might do in another video. For our final example, we will utilize all three units along with the recycled stream to showcase the situation when we have two streams that are both dependent on each other, which we would normally solve iteratively. We can also solve this iteratively in Excel by turning on Excel's iterative mode feature, which we will see. For this example, we have a simple setup where we would like to produce ammonia from hydrogen and nitrogen. However, due to the low single pass conversion of 25%, we would like to recycle most of our unreacted nitrogen and hydrogen back into the reactor while simultaneously producing a high purity ammonia product stream. We will first begin by solving stream 2, which is the outlet stream for a mixing unit operation. This is found by adding the components in stream 1 and stream 6 together. Note, stream 6 is a recycled stream, therefore stream 2 and 6 are both dependent on each other and will cause a circular reference error, which I will show how to resolve later, which will also result in us obtaining the solution to the problem. Stream 3 is not really a stream, it's just meant to showcase how many moles for a particular component are consumed or produced based on the inlet stream into the reactor, which is just the negative or positive part of the governing equation we looked at previously. Remember to change this part to the positive sign. We then simply need to add stream 3 and stream 2 together, which results in us obtaining the outlet stream for our reactor. Stream 4 then enters a separator to separate out our ammonia product that we have produced from the unreacted nitrogen and hydrogen, which results in us obtaining a bottoms high purity ammonium stream and a top stream mostly consisting of raw materials which we can recycle back into the reactor to produce more ammonia. So, as we have done before, we simply need to multiply the inlet stream by our split fractions. However, we see in this case it is not based on the top stream but the bottom stream instead. Therefore, to find the component flow rates in stream 6, we need to subtract stream 5, our bottom stream, from stream 4, our inlet stream. But as you can see, this results in a circular reference alert in Excel because stream 6 and stream 2 values are both dependent on each other, We can resolve this by turning on iterative calculation feature in Excel. Depending on how complex the system is, you may need to increase the maximum number of iterations and decrease the maximum change. However, this may result in calculations taking a lot longer to complete, which would vary from computer to computer. And with that, we have obtained our solution, and we can then take these results to further analyze. For instance, we may want to perform energy balances, and then maybe we might want to design the equipment for the entire process. Hopefully, I was able to showcase how useful Excel can be for performing these types of calculations. Thanks for watching. And if you have not already, please like and subscribe, and feel free to leave your comments on any content you may be interested in seeing in the future. Bye.